Hi, I'm Mark Boss, and in this video I will present NERD, Neural Reflectance Decomposition from Image Collections. The goal of the work is to create relightable 3D assets from unconstrained image collections. In other words, given a sample image collection as shown here on the left, we aim to estimate both shape and material properties resulting in a relightable 3D asset as shown on the right. Our method is based on NERV. Let's briefly recap NERV. NERV creates two coordinate-based MLPs which store the density and the view-dependent color at each position in the neural volume. NERV and our method train the two networks in conjunction. We start by looking at the first network, often called the coarse network. To generate the contribution of a single pixel, we cast a ray from the camera into the scene. We first apply a regular sampling pattern along the ray. We then evaluate the points along the ray. The evaluated color per point is also dependent on the ray direction. This color is then alpha composed based on the density of each sample. We then use the density along the ray to compute a sampling distribution. Further samples are then placed based on the distribution. All samples are then queried in the second network, the fine network. Here we break with NERV. NERV again alpha composes the view-dependent colors. Our method, on the other hand, alpha composes material properties that are not view or illumination dependent. These view and illumination independent material properties are the BRDF parameters, base color, metallic, roughness, and we also derive the surface normal based on the density gradient. Combined with a trainable spherical Gaussian illumination model, which can even be learned for each individual image, we then differentiably render the final output color, which is then view and illumination dependent. The rendered result is then used for the loss calculation with the corresponding color from the input image. As a recap, NERV is only capable of having view-dependent colors. NERD, on the other hand, learns view and illumination independent BRDF parameters and uses physically based rendering to calculate the visible color. As NERV is not capable of handling varying illumination, one can take inspiration from NERV in the wild. Here we extend the NERV model with an appearance embedding. However, note that the final color is only an interpolation of the scene illuminations and view directions. NERD, on the other hand, learns a view and illumination independent BRDF which can be relighted under any illumination and viewed from any angle. After training our neural volume, we propose to extract the model into a textured mesh. We first sample the volume and keep high-density points, extract the point cloud with the BRDF parameters, and filter it to remove outliers. We then create a textured mesh from the point cloud. The resulting mesh can be easily rendered in any game engine in real time, and we have interactive visualizations on our project page using a WebGL renderer. Let's inspect some results of the method. As already mentioned, NERV is not capable of relighting under unseen illuminations and can also not handle objects under varying illuminations. Here we showcase the expected inconsistencies. Compared with NERV, our method generates equally detailed and accurate results while having fewer floating artifacts. This is due to our physically constrained rendering used during the optimization. Numerical evaluations support our accurate reconstructions. First, we only look at fixed illumination from the real-world datasets. This means only a single illumination is present and the camera rotates around the object. As seen, all methods are comparable in performance while our method performs better than the baselines. On image sets with varying illuminations, NERV can now be seen as a weak baseline since it is not capable of handling varying illuminations. NERV-A, on the other hand, is a strong baseline as the task is simpler compared to creating an accurate decomposition. Still, our method works on par with NERV-A. In addition, our method is capable of relighting under unknown illumination and allows for real-time rendering. In summary, we propose a method which is capable of decomposing image collections under flexible capture setups. Due to the explicit decomposition, our method is capable of relighting under any illumination. Our mesh extraction step allows us to import the object into real-time rendering engines. The key to this is our spherical Gaussian illumination representation and our fast differentiable rendering. Thank you, and visit our project page where we have interactive results and further information.